periodic table, a grand design. Elements combine in patterns aligned. With every new concept we will unlock. Join the discussion, it's just Chem Talk. Chem Talk!
Welcome to Chem Talk, where we make chemistry, well, a little less intimidating, a little more exciting, Think less textbook, more like discovering a cool cheat code in your favorite game.
Yeah.
This deep dive, it's all about nomenclature.
Ooh, nomenclature.
No, I know it might not sound as flashy as scoring a power-up or something.
Right.
But trust me on this one. This is the secret code language that unlocks the whole world of chemistry.
Absolutely.
Think about it this way. In a game, you mix up the wrong ingredients, you're in for a disaster, right?
For sure.
But mixing up chemicals in a lab, that's a whole other level of game over.
Yeah, it's a whole different ball game.
So this is especially for you 10th graders out there, just starting your chemistry journey.
Yeah.
This deep dive, it's we're giving you a cheat sheet.
Absolutely.
For understanding all those weird and wonderful chemical formulas.
Could be good.
And we're going to discover how to name both ionic and covalent compounds.
That's right.
It's like learning different dialects for different chemical families.
Exactly.
So I guess a good place to start is with those chemical bonds.
That's right.
The ones we keep hearing about.
Yeah.
So ionic compounds, for example.
Okay.
They form when a metal and non-metal get together.
Right.
It's all about attraction
Right.
between opposite charges.
Like magnets, right?
Yeah.
Yeah.
We call the positively charged ions cations.
Right.
And those are usually metals.
Mm-hmm.
And the negatively charged ones, we call those angens.
Right.
And those are usually non-metals.
Absolutely.
So it's kind of like magnets, right? Opposites attract.
Exactly.
It's like that.
Like magnets, yeah.
So take sodium and chlorine, for instance.
Sodium and chlorine.
Sodium, the metal, that's our cation,
Uh-huh.
with a positive charge.
Right.
And chlorine, the non-metal, that's our anion.
Yep.
With a negative charge.
That's right.
They attract each other like crazy.
Oh, they do. They do.
Bam, you get sodium chloride,
Boom.
which is just like plain old table salt.
Exactly. That's all it is.
And the naming convention is super straightforward.
It is. It is.
Just name the sodium first,
Uh-huh.
then the anion with an "ide" ending.
That's right. So sodium chloride
Sodium chloride, yeah.
makes sense, right?
Okay, I'm with you so far.
Great.
But I've heard that some metals can be a little tricky.
Oh,
Like
yeah.
they have commitment issues or something.
That's a great way to put it, actually.
Yeah.
Yeah, some metals, what we call type 2 cations,
Okay.
they can have multiple charges.
Oh.
It's like we have different alter egos,
Right.
depending on who they're, bonding with.
Yeah.
And that's where those Roman numerals in parentheses come in.
Okay.
They tell us which version of the metal we're dealing with.
So it's like those RPGs where you can customize your character's abilities.
Uh-huh.
Different Roman numerals mean different powers.
Yeah.
But this isn't a game, right?
No.
Why is it so important to get those Roman numerals right?
You're absolutely right. Those Roman numerals, they're crucial.
Yeah.
In chemistry, a seemingly small detail
Yeah.
can make a huge difference.
Okay.
Let's take iron as an example.
Okay, iron.
Iron, written as Fe2, has a +2 charge, while iron, Fe2, has a +3 charge.
Oh, wow.
They might sound similar,
Right.
but they form completely different compounds
Okay.
with drastically different properties.
And confusing these two,
Oh, yeah.
that could be the difference between creating a life-saving medicine and a dangerous toxin.
Exactly.
Whoa, that's intense.
It is intense.
Okay, I am definitely paying attention to those Roman numerals from now on.
Good.
Okay, so we've got our single element ions figured out.
Right.
But what happens when we have groups of atoms acting like a single unit?
Oh, you're talking about polyatomic ions.
Okay.
These are like those super powerful raid bosses
Okay.
in video games.
Uh-huh.
They're groups of atoms that stick together and have an overall charge ready to bond as a single unit.
So instead of one lone wolf atom, we've got a whole gang rolling up
Exactly.
with a positive or negative charge.
That's right.
Ready to make some chemical bonds.
Ready to make them bonds.
I like it.
I like it too.
So a classic example is ammonium.
Ammonium.
NHA.
Yep.
Think of it as a nitrogen atom leading a pack of 4 hydrogen buddies. They're always together,
Always together.
always rocking that +1 charge,
That's right.
and always looking to bond with an anion.
Absolutely. Yep.
Okay, I can see how memorizing these common polyatomic ions
Uh-huh.
would be like a lifesaver.
For sure.
When it comes to naming compounds,
Yeah.
it's like having a cheat code
Absolutely.
for deciphering those complex formulas.
Totally.
You got it.
Yeah, it's like recognizing like a celebrity entourage instead of having to figure out like who each individual bodyguard is.
Right.
It makes naming compounds a whole lot easier.
So, all right, so we've tackled ionic compounds
Okay.
where electrons are transferred between atoms.
Uh-huh.
But what about those situations where atoms decide to, like, share electrons
Okay.
instead of going for a full-on ionic bond?
Excellent question. That's where covalent compounds come in.
Okay.
And these are more about collaboration
Right.
and sharing.
Sharing, yeah.
Just like a well-coordinated team in a video game.
I like it.
Instead of one atom, like taking all the electrons,
Uh-huh.
they decide to share
Right.
to achieve stability.
Okay.
Yeah.
So if covalent compounds are all about, like, sharing,
Yeah.
I'm guessing the naming system has to be, like, different too.
You're absolutely right. We need a way to, indicate how many of each atom are involved in this electron sharing party.
Okay.
And that's where those awesome Greek prefixes come in.
Okay, I remember learning about, like, mono, di, tri, all that back in, like, middle school.
Right.
But how do those prefixes, like, how do they help us with naming covalent compounds?
Okay, so they tell us exactly how many of each atom are present in the molecule.
Okay.
For example, CO is carbon monoxide, meaning there's one carbon atom and one oxygen atom sharing electrons.
So mono means 1.
Exactly.
Got it.
But if we add another oxygen atom to the mix, we get CO, carbon dioxide.
Okay.
Di means 2, so we know there are 2 oxygen atoms hanging out with that one carbon atom.
Whoa, just adding 1 oxygen atom completely changes the compound.
It does.
And I'm guessing that means carbon monoxide and carbon dioxide, like, act totally different too, right?
You bet. They have completely different chemical properties and behave very differently in the environment and in our bodies.
Okay.
That's why those prefixes are so important.
Right.
They're not just random words,
Yeah.
They give us crucial information about the composition of the molecule. It's like a recipe. If you use the wrong amounts of ingredients, you'll end up with a completely different dish.
Right.
And in chemistry, that could mean the difference between something harmless and something, well, potentially dangerous.
Okay, I'm starting to see why nomenclature is so important.
Good.
It's not just about, like, memorizing a bunch of rules. It's about understanding how those rules help us, communicate clearly and accurately about the chemicals we're working with.
Exactly.
So we've covered ionic compounds with their cations and anions, and we've talked about covalent compounds with their electron sharing and Greek prefixes. Are there any other types of compounds we need to conquer in this deep dive into nomenclature?
There's one more important category to explore, and that's acids.
Okay.
These are like those enigmatic characters in video games.
Okay.
They have a unique set of properties and require a slightly different approach when it comes to naming them.
Okay, color me intrigued. What makes acids so special? And how do we, like, crack their naming code?
Well, technically, acids are a type of covalent compound.
Okay.
But there's a twist. Hydrogen, usually our friendly question in ionic compounds, acts a bit differently in acids. It still wants to bond with a nonmetal, but instead of fully giving up its electron like a true metal, it shares its electron in a slightly lopsided way.
So it's like hydrogen's trying to be a cation, but it can't quite commit.
That's a great way to put it.
Yeah.
And because of this unique bonding behavior, acids have some pretty distinctive properties. For instance, they tend to taste sour, think, lemon juice or vinegar. And they can react with certain metals to produce hydrogen gas. Pretty cool, huh?
Definitely. But how do we know when we're dealing with an acid just by looking at, like, a formula? Is there some sort of giveaway?
Absolutely. Most acids start with hydrogen in their formula.
Okay.
And just like with ionic and covalent compounds, there's a systematic way to name acids based on the anion they'd form if hydrogen was a metal. So, for example, HCl is hydrochloric acid. It acts as though hydrogen gave its electron to chlorine, much like sodium does in NaCl. See how the name hints at the underlying formula?
Yeah.
That's the beauty of nomenclature.
Right.
It's a code you can crack.
Okay, that makes sense.
Yeah.
So the naming system for acids is kind of like a what-if scenario where we're pretending hydrogen is acting like a metal to help us figure out the name.
Right.
But I'm guessing there are some additional rules involved, right? Like, how do we deal with those "-ide, "-ite," and "-ate" endings we see in some anions.
You're sharp. You're right. Those endings play a crucial role in acid naming.
Okay.
It's like they unlock different levels in the game.
Okay.
If the anion ends in "ide," we use the prefix hydro and an ending acid.
Okay.
For example, HCl becomes hydrochloric acid.
Okay, that's pretty straightforward. So what about those "-ite" and "-ate" endings?
Okay, so anions ending in "ite" become acidic acid.
Okay.
For example, HNO is nitrous acid.
Okay.
And anions ending in "ate" transform into iic acid, like HNO, which is nitric acid.
Okay.
Notice how the names change slightly based on the number of oxygen atoms present in the ani? It's all about recognizing those subtle clues in the formula.
This is starting to feel like a puzzle where everything has its place. And the more we practice, the better we get at, like, solving it. But before we move on, I want to make sure I've got this acid naming thing down pat. Can we maybe try, like, a quick example?
Of course. Let's try HIs. Can you crack the code and figure out the name of this acid?
Okay, let's see. It starts with hydrogen, so I know it's an acid. The anion is SO, which I remember is sulfate. And since it ends in "ate," we change it to iic acid. So the name is sulfuric acid.
Yes, you nailed it. Sulfuric acid. You're becoming a true nomenclature ninja.
This is way more fun than I thought it would be. It's like I'm unlocking a secret language. But I do have one more question. We've been talking about polyatomic ions acting like these super bonded units.
Right.
But how do we know which atoms are going to, like, team up to form these groups? It's like they have some kind of secret pact while other atoms are perfectly content flying solo.
That's a great observation. And the answer lies in understanding the driving force behind chemical bonds, those tiny little electrons, and how they're arranged around an atom. You see, atoms crave stability, and they achieve that by having a full outer shell of electrons, usually 8. We call this the octet rule.
So it's like their electron configuration is their dating profile, telling other atoms what kind of relationship they're looking for.
Yeah.
Some atoms are all about sharing, while others are more interested in, giving or taking electrons to achieve that, like perfect 8.
Exactly. And those non-metals we talked about earlier, they're the ultimate sharers.
Okay.
They're really good at forming covalent bonds where they share electrons to achieve that stable octet configuration. And sometimes that sharing leads to the formation of these awesome polyatomic groups.
Okay, so when nonmetals get together, they're more likely to form covalent bonds, potentially creating those powerful polyatomic units. It's like they're forming alliances to conquer the world of chemistry.
I love that analogy.
Yeah.
They're all about teamwork, pooling their electrons together to create a stable and happy molecule.
This is all starting to click, but I'm still curious about those specific polyatomic ions. Are there any, like, hints or patterns that can help us predict what kinds of combinations are possible? Is there some sort of cheat code for figuring out these, like, ionic gangs?
There are definitely some trends we can observe. For example, a lot of polyatomic ions are what we call oxoanions, which are basically a central non-metal atom surrounded by a posse of oxygen atoms. Oxygen is like the social butterfly of the periodic table, always looking to bond and share electrons.
So oxygen is the popular kid everyone wants to hang out with. No wonder we see it in so many polyatomic ions.
You got it. And here's the cool part. There's a system for naming these oxoanions based on how many oxygen atoms are present. It's like those naming conventions in video games where you can tell a character's strength just by their name.
Okay, tell me more. I'm all about finding those hidden patterns and shortcuts.
Okay, so when we have 2 oxoanions for a particular element, the one with more oxygen atoms gets the 8 ending,
Okay,
and the one with fewer oxygen atoms gets the ite ending.
okay.
For example, no is nitrate, while no is nitrite. See the connection?
Yeah.
More oxygen 8 ending, fewer oxygen ite ending.
So it's like the 8 ion is the older, more experienced player, while the 8 ion is the rookie still leveling up.
That's a great way to remember it.
I like it.
And if we have an oxoanion with even more oxygen atoms than the 8 ion, we add the prefix, perchlorate chlor.
Okay.
And if it has fewer oxygens than the ion, we add the prefix hypochlorate chlor. It's like a whole ranking system based on the number of oxygen atoms.
Whoa. It's like a whole family of oxoanions, each with their own unique name and number of oxygen atoms. This is starting to make so much sense. I feel like I'm finally cracking the code of chemistry.
That's the power of nomenclature. It's not just about memorizing a bunch of random names. It's about understanding the logic and patterns that underlie those names. It gives you the tools to decode the language of chemistry and unlock a deeper understanding how the world works at a molecular level.
I have to admit, I came into this deep dive thinking nomenclature was going to be pretty dry and boring.
Yeah.
But it's actually been really fun and engaging. Who knew naming chemical compounds could be so cool?
I'm glad to hear that chemistry is full of fascinating discoveries discoveries waiting to be made, and understanding nomenclature is like getting a backstage pass to the amazing world of molecules and reactions.
Absolutely. So for all you aspiring chemists out there, don't be intimidated by nomenclature, like learning any new skill in a video game. It takes practice and patience, but once you master it, you'll be unstoppable. And a huge shout out to the Geeky Gamer science teacher for creating this awesome podcast. Let's go make chemistry ROCK.
Discussion, it's just Chem talk.